Determining the horsepower capacity of a switch hinges on its voltage and current handling capabilities. While the National Electrical Code doesn't offer a direct formula for horsepower calculation, we can approximate it using this equation: horsepower equals voltage in volts times current in amps divided by efficiency. Motor efficiency fluctuates based on its type and size. An efficiency of 85% is a reasonable estimate. For 600 amp switch operating at 480 volts, the calculation is as follows: horsepower equals 480 times 600 divided by 0.85, resulting in approximately 341,176 horsepower. Now let's discuss code considerations for motors used infrequently and managing different load scenarios. National Electrical Code Section 430.52 addresses motors used infrequently, permitting a maximum disconnect rating of 125% of the motor's load. Furthermore, National Electrical Code Section 430.53 allows connecting motors with varied horsepower ratings to a single disconnect, provided the total load doesn't surpass the switch's rating. It's vital to remember that when connecting multiple motors to one switch, the aggregate connected horsepower must be considered to prevent overloading the switch. Let's walk through an example calculation. Suppose you have a 600 amp switch, and you're connecting these motors. Motor 1 is a 50 horsepower motor used infrequently, motor 2 is a 100 horsepower motor, and motor 3 is a 75 horsepower motor. The total connected horsepower is figured like this: 50 times 1.25 plus 100 plus 75, which equals 237.5 horsepower. Since this total is significantly below the 600 amp switch's maximum horsepower capacity of roughly 341,176 horsepower, the switch can manage the connected load safely. In conclusion, you can estimate the horsepower capacity of a 600 amp switch using the formula we discussed. The code provides allowances for higher disconnect ratings for motors not used often and different load configurations. The bottom line is always ensuring the total connected horsepower remains within the switch's limits. The NEC Section 430 covers motor circuits, motor overload protection, and motor control circuits, providing comprehensive guidelines for safe motor installations. When determining the appropriate size for conductors feeding motors, refer to NEC Table 430.22, which specifies the minimum ampacity of conductors based on the motor's full load current. For motor overload protection, NEC Sections 430.31 through 430.43 outline the requirements for overload devices like thermal overloads or electronic overload relays, protecting the motor from damage due to excessive current draw. For sizing fuses or circuit breakers for motor branch circuits, NEC Section 430.52 provides guidance on the maximum allowable rating or setting of the overcurrent protective device, ensuring proper short circuit and ground fault protection. When dealing with multiple motors connected to a single feeder, NEC Section 430.24 outlines how to calculate the feeder ampacity considering the sum of the full load currents of all motors plus any additional loads. When sizing motor starters and controllers, NEC Article 430 Part C covers the requirements, including the controller's horsepower rating and its ability to interrupt the motor's locked rotor current. For motor disconnecting means, NEC Sections 430.101 through 430.110 specify the requirements for disconnecting switches or circuit breakers, ensuring a safe means to energize the motor for maintenance or repair. When installing motors in hazardous locations, NEC Article 500 provides additional requirements for explosion-proof or intrinsically safe motors and related equipment. For energy efficiency considerations, NEC Section 430.12 outlines requirements for energy-efficient motors, promoting energy conservation and reducing operating costs. For motor control centers, NEC Article 430 Part H covers the installation requirements, including spacing, wiring, and grounding, ensuring safe and reliable operation of the motor control center. Remember to consult the latest edition of the NEC and follow all applicable local codes and regulations for safe and compliant motor installations. Always consider factors like ambient temperature, voltage drop, and motor service factor when selecting conductors, overcurrent protection, and control equipment for motor circuits. Proper grounding is essential for motor installations, and NEC sections 250.110 through 250.126 provide detailed requirements for grounding motor frames, enclosures, and raceways. When using variable frequency drives or VFD to control motor speed, be sure to follow the manufacturer's instructions and NEC Article 430 Part J, which covers the installation and wiring requirements for VFD. Regular maintenance and inspection of motor circuits and equipment are crucial for preventing failures and ensuring safe operation. Keep motor enclosures clean and free from debris, and periodically check for loose connections, damaged insulation, and signs of overheating. Always de-energize motor circuits before performing any maintenance or repairs, and use appropriate personal protective equipment or PPE to protect yourself from electrical hazards. When troubleshooting motor problems, use a systematic approach, starting with the simplest checks first, such as verifying power supply, checking for tripped overloads, and inspecting wiring connections. If you encounter complex motor problems, consult a qualified electrician or motor repair specialist for assistance. By following these guidelines and adhering to the NEC, you can ensure the safe and reliable operation of motor circuits and equipment. Always prioritize safety and consult with qualified professionals when working with electrical systems. The formula for horsepower, as previously mentioned, is an approximation. A more precise calculation might require considering the motor's power factor. Power factor is the ratio of real power absorbed by the load to the apparent power flowing in the circuit. It's a dimensionless number between 0 and 1. An ideal power factor is 1, meaning all the power supplied is used effectively. A lower power factor indicates that a significant portion of the power is reactive and doesn't perform useful work, increasing the overall current draw. If the power factor is known, the horsepower formula can be adjusted to horsepower equals voltage in volts times current in amps times power factor divided by efficiency. This provides a more accurate estimate of the motor's actual horsepower output. Reactive power compensation, often achieved with capacitors, can improve the power factor, reducing the current needed for the same amount of real power. This is particularly important in industrial settings with many inductive loads like motors. When dealing with multiple motors, consider the impact of motor starting currents. Motors draw a significantly higher current during startup, known as inrush current or locked rotor current. This inrush current can be several times the motor's full load current, potentially causing voltage dips and nuisance tripping of circuit breakers. To mitigate this, various techniques are used, including reduced voltage starters like auto transformers, part winding starters, or solid-state soft starters. These methods limit the starting current, reducing the impact on the electrical system. Another important consideration is the motor service factor. The service factor is a multiplier that indicates how much overload a motor can handle for a short period without damage. For example, a motor with a 1.15 service factor can handle 15% more load than its rated horsepower for a limited time. However, operating a motor continuously above its rated horsepower, even within the service factor, can shorten its lifespan. When selecting a motor, it's essential to match the motor's horsepower and service factor to the application's requirements. Also, consider the motor's enclosure type. Motor enclosures are designed to protect the motor from environmental factors like dust, moisture, and hazardous materials. Common enclosure types include open drip proof or ODP, totally enclosed fan-cooled or TEC, and explosion proof. The appropriate enclosure type depends on the motor's operating environment. For example, in dusty or wet environments, a TEF motor is preferred. In hazardous locations where explosive gases or dust are present, an explosion-proof motor is required. Motor insulation class is another critical factor. Motor insulation is designed to withstand heat and voltage stress. Insulation classes are designated by letters like A, B, F, and H, with each class corresponding to a maximum operating temperature. Higher insulation classes can withstand higher temperatures, allowing for longer motor life and improved reliability. It's important to select a motor with an insulation class appropriate for the application's operating temperature. Overheating is a major cause of motor failure. Proper ventilation and cooling are essential for maintaining motor temperature within acceptable limits. Ensure that motor cooling vents are not blocked and that the motor is not installed in a confined space with an adequate airflow. Regular cleaning of motor cooling fans and heat sinks can also help prevent overheating. Vibration analysis is a valuable tool for detecting motor problems early. Excessive vibration can indicate issues like bearing wear, misalignment, or rotor imbalance. Performing regular vibration analysis can help identify these problems before they lead to catastrophic failure. Motor efficiency standards have become increasingly stringent in recent years. Energy-efficient motors, also known as premium efficiency motors, are designed to reduce energy consumption and operating costs. These motors typically have higher efficiencies and lower losses than standard efficiency motors. When replacing motors, consider upgrading to energy-efficient models to save energy and reduce your carbon footprint. Harmonic distortion can also affect motor performance. Harmonics are unwanted frequencies in the electrical system that can cause overheating, vibration, and premature failure of motors and other equipment. Harmonic filters can be used to mitigate harmonic distortion and improve motor performance. Proper grounding is essential for motor safety and performance. A properly grounded motor frame provides a low impedance path for fault currents, protecting personnel from electric shock and preventing damage to equipment. Follow NEC guidelines for grounding motor frames and enclosures. Surge protection is also important for protecting motors from voltage spikes caused by lightning strikes or switching transients. Surge protective devices or SPD can be installed to divert surge currents away from the motor, preventing damage to the insulation and other components. Regular motor testing is recommended to assess motor condition and identify potential problems. Common motor tests include insulation resistance tests or mega tests, winding resistance tests, and surge comparison tests. These tests can help detect insulation breakdown, winding shorts, and other defects. When troubleshooting motor problems, use a systematic approach. Start by verifying the power supply, checking for tripped overloads, and inspecting wiring connections. Use a multimeter to measure voltage, current, and resistance. If the problem is not immediately apparent, perform more advanced tests like insulation resistance and winding resistance tests. Always follow lockout-tagout procedures before working on motor circuits to prevent accidental energization. Lockout-tagout involves disconnecting the power supply and placing locks and tags on the disconnect switch to prevent it from being turned on. This is a critical safety procedure that can prevent serious injury or death. In addition to the NEC, other standards and guidelines may apply to motor installations, such as those from the National Electrical Manufacturers Association or NEMA and the Institute of Electrical and Electronics Engineers or IEE. Consult these standards and guidelines for additional information on motor selection, installation, and maintenance. Remember that working with electrical systems can be dangerous. Always follow safe work practices and consult with qualified professionals when necessary.